Go ahead and look at these. Don't write them down, but talk to your group about any patterns that you see. How do you get from term to term in these?
It's like 1, 2, 4, 8, 16. So that's ours. And then the bottom is 3, 9, 2, 7. I was like so confused.
So now that that's a 48, what's happening in that one?
Doubling.
It's doubling. So we're multiplying by 2 every time? What about the second one?
Multiply by 3.
Ah, we're multiplying by 1/3. What about that third one? We'll come back to that one. Okay? What? Not a fan? You don't like it? These are what we call geometric sequences. Why are they geometric? Because from term to term, what are we doing? We are multiplying by the same number. Yesterday we were adding the same number. Today we are multiplying the same number. A geometric sequence is a sequence whose consecutive terms have a common ratio. That number that we keep multiplying by, we call it the common ratio. Okay? Just like yesterday, we have a specific way we are going to write geometric sequences. Okay? If you have a sequence where you are multiplying by the same number over and over and over, we can go ahead and use this explicit definition to write the rule. Okay. So our nth term is, what does this mean right here? The first term times r to the n minus 1. R is our common ratio. We multiply it to each term. So to get from like the first to the third term, we would have to multiply by r twice. So to get our third term, we would have our first term times r squared. That's why this formula is the way that it is. So, knowing that this is how we need to set up our formula, let's go back to that first example. 6, 12, 24. Gosh, darn it, I'm going to just have to go fix these when we're all done. 48, 96. If you don't have it written down, go ahead and write those 5 numbers down right now. Zach, what number are we multiplying by each time?
Multiplying 6 and we're doubling it each time.
Okay, so from term to term, we are multiplying by 2, which means our common ratio is 2. Okay, so if we want to write the nth term, we're going to take our first term, which is 6, and then multiply it by our common ratio to the n minus 1. What kind of function could this be compared to? An exponential function. Okay, good. All right, let's go back to that second sequence that we were looking at. If you don't have it written down, go ahead and do so. 972, 324, 108, 36, 12. Jen, what number are we multiplying by over and over and over?
Well, we're dividing it by 3.
Okay, so since we're dividing by 3 from term to term, we can say that we're multiplying by 1/3, right? So if you recognize that we're dividing every time, we can just switch it to multiplying by whatever fraction, okay? So we're multiplying by 1/3, that's our common ratio. So if we are going to write the explicit definition, we are going to say that a sub n is our first term times our common ratio, excuse me, to the n minus 1. Let's find the 10th term. And we may need our calculators for this. If we want to find the 10th term, Hannah, what do we need to do?
Plug in 10.
Yep. So if I were you, I would plug in 972 times 1/3 raised to the 9th power. That 1/3 is going to need to be in parentheses for all of it to get the power. Okay. Since we are working with fractions, I'm not going to really want a decimal answer here. So use the math function in your calculator to get it from decimal to fraction if it is one. Okay. Connor, what did you get?
4 over 80.
4 over 81. Good. Before I release you for lunch, we're going to write the recursive definition. Okay? As always, for recursive definition, we have to define the first term. And then, since from term to term we are multiplying by the same number, that means we need to take our term previous and multiply it by that common ratio. To get from one term to the next, we multiply by the common ratio. When you get back from lunch, we will do another example, and then we will talk about summations. Here is the one that was on the front slide that we weren't really sure about. I will tell you that it is geometric. can we figure out the common ratio? What are we multiplying by each time? There you have it.
2/3 times -1 to the n plus 1 power.
Okay. So there's that like switching back and forth, right? What we can do you have something that you would
Could you make it -2/3? Because you're taking the first one and then like you're putting the negative to a power anyways, so it'll switch by itself.
Okay, yes, so since we are going to take our r to the power, it is okay to identify our common ratio as -2/3 because we're multiplying by -2/3 to get from term to term, and that will cause our signs to flip, okay? So if it's not geometric, we would need that -1 to the n power or n plus 1. Since the r gets raised to the n minus 1 power, we can group it all together. Okay? So if we are going to write the explicit definition, also known as the nth term, we would write 1/2 times -2/3 to the n minus 1. Go ahead and find me the 10th term, please. Amanda, what do you get?
My calculator didn't give me a fraction. I'm guessing my answer.
Can you say math fraction?
No, it's
It doesn't.
too rational.
It's too good.
It's too big?
Small.
Too small? Oh, shoot. Okay. What'd you get?
Negative 0.01300617.
That's what you got? And I won't change it to a fraction? That's very disappointing.
What was the fraction?
Yeah, with the way you're thinking.
Well, I didn't actually punch it into my calculator before right now. So, I mean, you could always do like 2 to the 9th and 3 to the 9th, and but if your calculator will not turn it into a fraction, then fine, we'll do the decimal. Okay. Oh, that should go there.
12 over 39366.
Okay. Our recursive definition. Okay. Remember, if we write something recursively, we identify the first term. And then Henry, how would we write the nth term for a recursive?
A n minus 1 negative 2/3.
Do you agree with Henry? Do you agree with Henry? Yes, okay.
We want to put the 2/3 at the end, or not in parentheses, and then
Yeah, I don't care if it's multiplied to the front or to the back of a sub n minus 1. As long as it's multiplied, that's all I care about. Okay? All right, we had a problem similar to this yesterday, but now I am telling you that it's a geometric sequence. Our second term is -18, our fifth term is 2/3, and we want to know the sixth term. what do we need to know about our sequence in order to find the sixth term? We need the common ratio, and then we can't find the first term unless we have that common ratio. Excuse me. So, if we know that the second term is negative 18, and the fifth term is 2/3, how might we be able to determine that common ratio? 30 seconds, brainstorm with your time.
You can just do negative 18 minus x equals.
All right, everyone back together. 5-4, do you have anything for us? Nothing? Not even an idea.
Well, I don't think it'll be the exact same as it was yesterday. We're not dealing with addition and subtraction.
Okay, what are we dealing with? We're dealing with multiplication, okay? So that's good. And how many terms are in between? 3, okay? 5-1, did you have an idea?
Ours wasn't very mathematical, but I just said just like messing
Okay. So just playing around with numbers is what you would try to do, okay? Does anybody have like a systematic way that they would go about doing it? More like an algebraic way?
You could have negative 18 and then have x be your common ratio, so you just multiply x till that gets you to the fifth term, and that would have to equal 2/3.
Okay, so we could take negative 18 and multiply by our common ratio 3 times to get to our fifth term. Okay? Since there are 3 terms between 2 and 5, we have to multiply by our common ratio 3 times to get to the fifth term. Make sense? So we have negative 18 r cubed equals 2/3. All right? What happens when we take 2/3 divided by negative 18? Ooh, that's nice, isn't it? Okay. If r cubed is negative 1 over 27, then r is negative 1/3. So now what we need is the sixth term. Now conveniently, we already know the fifth term. So how do we go from the fifth term to the sixth term? So we can take 2/3 times negative 1/3, and our sixth term is negative 2/9. Now, if they had asked for like the 15th term, we would need to figure out what our equation was. We would need to figure out that first term before we could plug in to find like the 15th term. If we needed to write the rule, how would we do that? If we needed to write the rule, how would we do that? How would we determine the first term? Caroline?
Could you just, I was gonna say you could set it up like a to the n equals a to the 1 and then put negative 1/3 and minus 1, and then you can like solve it out.
Okay, so we know that our rule needs to be this. Okay.
Maybe you could like put in a value you know for n, and then
Exactly. We could like put in a 5 for n, which means this would be 2/3, and then we can solve out what that first term is. Good. Okay. We have wrapped up geometric sequences. Now, tomorrow, when we do problems together in class, you are going to have to determine whether a sequence is geometric or arithmetic before you go writing the rules. You can't assume. Now, in your homework tonight, I think most of them are going to be geometric. But tomorrow, when we're mixing them up, we're going to have to really be sure to look at the pattern to determine whether it's geometric or arithmetic. Okay. All right. Geometric series. Here's how we find a finite sum for a geometric sequence. Okay, so here's our geometric sequence summed up to n number of terms. Here's how we find it. Okay, so you have your first term times 1 minus r to the n, and it's how many terms we have all over 1 minus r. Okay, this is not a difficult formula to set up, but you need to be very, very, very careful when you are typing it into your calculator. Okay. So go ahead and write down this series right here. Gabe, how many terms are we adding together? We're adding 12 terms together. We're going from 1 to 12. Okay? So, since this is geometric, how do we know that it's geometric? Okay. A number times a number to the power. Okay? It should look like an exponential equation. Okay? So to sum this up, we need the first term times 1 minus r to the n over 1 minus r. Okay, so Gabby, what is our first term? Our first term is 4 times 1 minus r to the n. So Molly, what is r? R is 0.3. And Gabe already told us that we have 12 terms. Okay. So if I were you, I would figure out that numerator first, and then I would divide it by the 0.7, and then multiply by the 4. You can put it in your calculator all at once, as long as you are careful with your parentheses. Did you put it in your calculator? That's a, I kind of had it squished in there. It's the exponent for 0.3. Sorry.
Okay.
Darby, you and Caroline looks like you're checking each other's answer. What do you get?
I got 5.714.
Do you agree with Darby? Yeah? Okay. If you are not getting that, let me know so I can help you with your calculator. Who did not get it?
Okay, so this is saying divided by 1 and then subtract. So what you're going to want to do is take divided by parentheses 1.
Perfect. So let's set this one up. Yes or no, everybody all together, is this geometric?
No.
Because the number you multiplied is 1.
I mean, it could. That wouldn't be.
Do we have a number to a power?
Yes.
So yes. Times 1. Okay, so that a sub 1 is 1. Okay, this is geometric. If it looks like an exponential function, it's going to be geometric. Okay, so our first term, I know there's nothing in front of it. We can say it's being multiplied by 1. So the first term is 1. 1 minus 2 to the 7th over 1 minus 2. Our sequence is doubling numbers from term to term. So this is probably going to be a fairly large number. Did you get there? 254 and 127. Mm. 127, are we getting that? Okay. So now I promised that we would talk about the infinite series again. Okay? Now, I want you to think about a geometric series. If we multiply by 1/2 every time, is that a geometric series? Okay. So I want you to imagine me in this door. Okay? I want to add up my distance, the distance that I walk, when I cut my distance in half each time. Okay? So I took this step, I cut my distance in half. I'm going to cut my distance in half again. I'm going to cut my distance in half again. I'm going to cut my distance in half again. Am I going to ever reach the door?
No.
No. But can you measure my distance that I travel? I'm never going to technically reach the door, but I'm going to get so darn close to the door that I'm basically there. You see what I mean? Okay. So we can add up an infinite number of terms of a geometric sequence under one condition. The absolute value of r has to be less than 1, like me cutting my distance in half. Okay? Now, if we were to have, if we were to double our distance, those numbers are going to get bigger and bigger and bigger and bigger. That's not going to add up to be anything. It's just going to be infinity. As long long as the absolute value of r, okay, because it can be positive or negative, is less than 1. Yes, I did.
What's about other costs?
Okay. I'm having like congestion issues, so my hearing's kind of weird. I didn't know if I was imagining that. Now, I want you to notice something about the formula that I have up here. You will sometimes see a geometric series begin at 0, and you will sometimes see a geometric series begin at 1. It doesn't matter where it starts. When you use the formula, just make sure that this is the first term and this is r. Okay? Is this geometric? Yes or no? Yes. Okay. Now it starts at 0. That's not a problem. Okay. If it starts at 0, then you're going to see this as an n instead of an n minus 1. That's just going to be the only difference. Now, is our common ratio less than 1? You betcha. So we can take the first term over 1 minus r to get a sum. We have 5 divided by 1/2. What you?
Mine says 0 underneath the sigma.
That's just a starting point.
Because it's starting at 0 instead of 1. You're going to see that. Sometimes you'll see geometric series start at 1. Sometimes you'll see them at 0. What about this series? We already decided that the sequence was 6 times 2 to the n minus 1. If we sum up the infinite sequence, okay, we can't actually do this one. Our common ratio is bigger than 1. This is just going to diverge to infinity. That's a smiley face, because you don't have to do any calculations.
So all of you guys need to be done.
You could write infinity. That would be fine. All right. Your homework is on your gold sheet. Keep in mind we have a quiz Friday. Your book work is your preparation for your quiz. Tomorrow we're going to look at some really cool, more applicable examples that deal with sequences and series. Okay? So I need you to come with your homework done, ready to go.